Welcome back, and today we are going to continue our discussion on different properties of Laplace transform, and this will be pretty much the end of our discussion on Laplace transforms, because this is kind of supposed to be a recap for you. I mean, of course, we studied quite a bit regarding Laplace transforms and different properties of Laplace transforms, and here we're going to end our discussion with quite a few important notes on Laplace transform, and we are going to see how we apply Laplace transform for our practical purposes. So with that said, again, we are not going to solve complicated problems that you probably used to solve in your mathematics classes. I mean, we are going to only do things that are pretty much necessary for our course on control system engineering here. All right, and we are going to assume a few things based on the fact that we only consider causal linear time invariant systems for our purposes, and based on that we are going to assume a few conditions. With that said, let's continue our discussion, and we are going to start with the convolution property. And I believe I told you we proved the convolution property, okay, in an earlier one here during the series on Laplace transform. So essentially what it tells me is that if there are two signals xt, let me just say, so this is the convolution property. Okay, essentially it tells me if there are two signals like this, xt, say, and gt, and if we convolve them, and what is the convolution? Essentially, if gt is the impulse response of a system and xt is the input to the system, then this convolution actually essentially produces the output. Okay, now we are not looking at the output here. We are looking at the Laplace transform of this convolved signal. We did prove that this would be essentially xs multiplied with gs, something like this. We actually this is something we actually proved in one of our earlier discussions, right? Because this property is one of the fundamental building blocks behind our transfer function algebra. All right, again, during the class, if you encounter any issue or if you find something difficult to understand, feel free to ask. I regularly see some of you only joining at the beginning and then leaving right after the start of the stream. So I notice you people, but I really don't care in that case. If okay, point is, no one can make you learn, right? I can only help you learn. All right, so with that said, so this is the convolution property. We proved this earlier, right? Okay, like 2 or 3 streams before this one, we actually proved this one, right? That's fine. And today we're going to use this property, the convolution property. So essentially, we're going to use the convolution property to derive one important property today. All right. All right. And that property is the time integral property. So again, if you recall, we derived the time derivative property, right? And we said the time derivative property is one of the most important properties, and also time integral property will also be one of the most important ones. So time integration property. Okay, what is the time integration property? Time integration property is this one. Look very carefully. It says, so my again the same type of question stands here. If the Laplace transform of xt is known to be xs, then now question is, what is the Laplace transform of this integral? Okay, so what is the Laplace transform of this integral? Okay, and now some of you might tell me that, okay, whenever this variable t is appearing in the limit, some of you might tell me, okay, fine, then in that case you are supposed to put a tau here, I do agree to that one. So that's not an issue. Okay, the same point stands. Essentially, what you are doing, you are integrating this function. You could write t k whatever. So, for example, if you write k, who knows? So essentially, you are going to integrate this signal and put the upper limit as t and the lower limit as negative infinity. So essentially, what this is, so let me just write xt. Essentially, what this is, imagine a signal. Okay, imagine a signal that has been there for a very long time. I mean, not necessarily a causal signal. Maybe that has been there for a very long time, something like that. And say, I mean, this is the future for the signal. Okay, and imagine this is the current instance. So this is at this moment, this is t, right? This is the current instance. So what happens, this integral essentially means, so for example, this is my xt, this is the signal. So this integral essentially means that we are integrating over the entire history of the signal. So essentially, up until the present instance, we are essentially integrating the entire signal. So we are trying to find out the area under the entire curve up to present instance. So up to the present time, exactly. So up to this point, so up to the present instance, or up to this point, what is the total area? What has been the total area under the signal? Something like that. What has been the integral of the signal, right? And you would see something very interesting. So now we are kind of looking for the Laplace transform of this one. Maybe we don't know it yet. Okay, we don't know it yet. We are trying to derive this expression, right? So let's try to do that. So, but we are going to approach this problem slightly differently, and you would see how this actually turns out. We are going to approach this problem slightly differently, and you will see that this is slightly nice in this regard. Okay, and we are going to, of course, draw analogy from our discussion on linear time invariant systems. All right. With that said, recall our convolution property. Say again, recall our convolution property. Recall the convolution property. Someone is saying upper limit. Why is the upper limit not infinity? Yeah, you see why the upper limit is not infinity. Why for the real integration or the time integration property? Why the upper limit is not infinity will be evident shortly. Okay. Recall that convolution property. What is the convolution property? The convolution property says this is, and just one more thing. If you integrate it up to infinity, what happens? This function no longer remains a function of t, right? This becomes a constant value, right? Since if this is a function of t, then if you integrate from minus infinity to infinity, this no longer remains a function of time, right? It becomes a constant value. So then there is no point of taking a Laplace transform, right? If I integrate up to t, then it still remains a function of t, right? Okay. So the convolution is convolution. Again, we just write the definition of convolution. So recall the definition of convolution. If you recall, then this was the definition of convolution. We did elaborate discussion on convolution. I also handed out with proper manuals and everything. So recall, this was the integration we actually did to calculate the convolution of two signals. Essentially, what is this? This is essentially, if I have a system whose impulse response is gt, if I have a system whose impulse response is gt, and I excite the system with an input which is xt, then the output of the system, which is yt, would essentially be xt converted with gt. Essentially, that is the thing, right? Now, of course, if I take Laplace transform on everything, then this becomes a multiplication in Laplace transform. Okay, also happens in Fourier transform as well. Now, with this said, with using this property here, this convolution property, okay, imagine now, consider gt, that is the impulse response of the system, to be a unit step signal. Imagine the system that we have has an impulse response of unit step, right? Imagine the impulse response of the signal to be a unit step. If that is so, okay, so of course, what does the system, what does it mean? It means that if I provide an impulse in the system, okay, then the output would be a unit step, because that's the impulse response of the system, right? So if the impulse response of a system is unit step, it means when I excite the system with an impulse signal, the output would be a unit step. With that said, then we have xt convolved with ut, and that essentially becomes integration from minus infinity to infinity x tau u t minus tau d tau. Now look at this, ut minus tau d tau. Let me draw it. Now of course the independent axis is now tau, right? Again, right? You know this already. So this is, imagine this is tau, right? All right, so here is your u tau. All right, so this is your u tau, no problem, right? It's a unit step signal, just as usual, right? Question is, how do I derive this? Again, remember that t is a constant here. As far as this integration is concerned, t is a constant, okay? Because tau is the variable for the integration here. All right, then what is u minus tau? Of course, if this is u tau, what does u of minus tau look like? This would be a time flip essentially. So let's do a time flip on the signal. So that is what the signal would look like after a time flip, of course. So that would be u of minus tau, right? And essentially what ut minus tau essentially means is that it would be a right shift or a left shift depending on the value of t. If t is positive, then this would be a right shift. If t is a negative quantity, then that would be a left shift, because we have done a time flipping. Again, we are just bordering into things that we studied in our last semester. Okay, so this would be something like, say, u 5 minus tau, where t is equal to 5 essentially something like this. Okay, if t is negative, then the shift would be on the left hand side, something like that. Okay, so this is t. If this t is here, then this is u t minus tau, and of course this has been there since negative infinity there. Okay, so that is u t minus tau, this signal, right? Good, no problem, right? But with this information, we can now write something slightly more interesting. Now with this information, now with this we can say, oh, let me just do one thing. Okay, fine. With this we can say that, look at this integration, right? This integration was from minus infinity to infinity, and this was x tau u t minus tau and d tau. And look at the limits. Limits are from minus infinity to positive infinity, right? All right. Now what about ut minus tau? What about this signal? We have just seen ut minus tau, this signal. Now this is there from negative infinity. So because this is like negative infinity, this is going to negative infinity. The value of the signal from negative infinity is 1. So this is 1. Okay. But the value of the signal remains 1 up until tau is equal to t. The moment tau becomes greater than t, the value of the signal becomes 0, right? The value of the signal becomes 0 essentially, right? A simple u tau would have a value of 0 if tau is negative, and if tau is positive, then u tau would have a value of 1. And for ut minus tau, okay, it would have a value of 1 as long as tau is less than t. So essentially I can write now ut minus tau. So this is the last plot here. So essentially ut minus tau, essentially this would have a value of 1 if our tau is less than t. As long as tau is less than t, that would be nice, and it will become 0 if tau is greater than equal to, okay. So that's pretty understandable, right? So this is essentially what we have drawn here. So essentially the tau limit here, look at the limits. The limit for tau for this integration varies from negative infinity to positive infinity, right? So now let's split the integration into two portions here. Okay, so one portion we are integrating from negative infinity to t. So we are writing x tau u t minus tau d tau, and then plus we are integrating from t to positive infinity. So we have split the integral from minus infinity to plus infinity into two subdomains like that. So we have x tau u t minus tau d tau. Okay, so this is the two portions of the integral. Now look at this portion is fine, but what about this portion? Now when tau is between t and infinity, which is essentially tau is greater than equal to t, ut would be equal to 0, right? Ut would be equal to 0. So this entire integral has to be 0 because one of the factors is 0 and that is being multiplied with everything. So this integral this part has to be 0, right? Because when tau, so here tau is greater than t because the limits are from t to infinity. So, and when tau is greater than t, ut minus tau is 0. So this part is 0. And what about this portion? In this portion, this has the value of 1, right? This has the value of 1. Because why does it have a value of 1? Because of this, because of the very definition of ut minus tau. So on the next line, I can write, so on the next line, this actually becomes 0. And here, what I can write is, this becomes just 1. This just becomes 1. So essentially, this becomes an integral from minus infinity to t on x tau d tau. Alright. So this becomes integral minus infinity to t x tau d tau. Again, since tau is a dummy variable, I could write t or something like that. So let's change our problem here. I told you earlier, moments ago. So it could be written x tau because just a dummy variable. Naming doesn't matter really. So now what we have essentially derived is that again, if you have any query, feel free to ask. We have essentially derived so far is that if I convolve our xt signal with a unit step signal, then it essentially becomes this integration from minus infinity to t x tau d tau. The convolution with unit step essentially becomes this. But from the convolution property of Laplace transform, we know this, that the Laplace transform of the convolution of two signals, in particular here we have xt and ut, is the product of their individual Laplace transform, that's xs and us. All right. So now right, but we have just derived that for this particular case, that convolution of xt with ut is essentially this integral. So essentially what we are trying to figure out is the Laplace transform of this integral So essentially integral from minus infinity to t x tau d tau, right? That's the Laplace transform of x tau d tau, Laplace transform of x tau d tau integrated from negative infinity, x tau integrated from negative infinity to t, like that. So what is xs? Yeah, that's the Laplace transform of xt. And what is us? I actually know us. What is us? That's the Laplace transform of ut. What is the Laplace transform of ut? That's 1 by s. Okay, that's 1 by s. So essentially this can be properly written as xs divided by s. So we have completed our proof per se. So what was our problem here? So we are now using we are now saying okay, proof here. So what we have derived is that if we do a time integration on the signal, the result is essentially this. If the Laplace transform of a signal is xs, then the Laplace transform of the time integration up to time t would be xs by s, and that's that is supposed to happen, right? So essentially now what we have figured out is that with this what we have figured out is, now look, now recall that the Laplace transform of xt was just xs. Now if we differentiated xt and took a Laplace transform on it, that was just s into xs. Okay, and now we have figured out that the Laplace transform of the integral of the signal that would be 1 by s into xs. Now with that understanding we have figured out all these things, right? We did this in the last one and we proved this today. And of course this has a condition, that zero initial conditions. Alright, so with this we can say, now if I differentiate in the time domain, this is essentially a multiplication with s, and if we integrate in the time domain, then it is essentially a multiplication with 1 by s or division by s. So this s, yeah, so someone is asking, in the place of x tau can I write t? Yes, you can write t, because that's a dummy variable. You can write lambda, you can write t, you can write whatever, right? Because after the integration you are going to place the limits anyway. So essentially look very carefully what happens. A multiplication with s essentially means a time derivative. A division by s essentially means a time integral. So multiplying xs, or that is the Laplace transform of anything, with s essentially differentiates the signal xt with respect to t, and dividing xs by s essentially integrates xt with respect to t from negative infinity to, got it? So that's kind of our understanding. So we just simply say s is kind of a differentiator and 1 by s is kind of an integrator. We say s is kind of a differentiator and 1 by s is kind of an integrator. Okay, right. All right. All right. So recall we started this entire discussion with essentially this system analogy, right? We considered a system whose impulse response was ut, right? Now look at this one. So we essentially started this discussion with a system whose impulse response was ut, and this got an input of xt, right? So essentially what we had was something, a configuration like this, of course, okay, that resulted into an integration. So what we even actually had was this one. For this particular example, the impulse response was ut, the input was xt, and the output essentially turned out to be something like this. So the integral of this, right? All right. And of course, if I take Laplace transform on all of these, what would be the Laplace transform of the impulse response? That's 1 by s. So this is, what is this? This is the transfer function of the system. What is this? This is xs. And what is this? This is ys. And what would this ys be? We just derived moments ago. That would be ys divided by s essentially. So 1 by s, okay, acts like a transfer function that integrates a signal, right? So 1 by x acts like a transfer function that actually integrates a signal, right? So if I have a system which has a transfer function of 1 by s, it would integrate a signal, right? So the point being that 1 by s, so gs equal to 1 by s, acts as a transfer function that integrates the input signal, right? So 1 by s acts as a transfer function that integrates the input signal, and that is why it's called an integrator. Thus, an integrator, a system that can integrate a signal, has a transfer function of gs equal to 1 by s. So the transfer function of an integrator is 1 by s. Again, very similarly, if we put s here, whose transfer function is s here, then the input is xs, the output would simply be s into xs. But when do I get s multiplied with a signal, with a Laplace transform? When the signal is differentiated, right? Essentially the output yt would be a time derivative of xt, right? So this s acts as a differentiator. So with the same vein, I can just copy paste my writing here. That, so here gs equal to s, that simple transfer function acts as a transfer function that differentiates the input signal. Thus a differentiator has a transfer function of gs equal to s. That's it. So this is called an ideal differentiator. This is called an ideal integrator. So ideal differentiator, so an ideal differentiator would have a transfer function of s. An ideal integrator would have a transfer function of ideal integrator would have a transfer function of 1 by s. All right. Oh, sure. Somebody got a mistake here. Absolutely correct. So you people are following this correctly. Fantastic. Nice. All right. So we have discuss things in terms of ideal properties. Now, of course, I believe you have studied op-amps in your analog electronics classes, and even if you didn't, we shall have a small kind of a recap on op-amps, and then we are going to learn how we actually can use op-amps as something called analog computers. Before there were digital computers, there used to be analog computers, and I would suggest you go to the internet and search for analog computers. You would see that before there were digital computers, there were analog computers. And what were analog computers? Essentially op-amp based circuits that could be used to solve differential equations, right? Back in those days, people still needed to solve differential equations numerically, and solving them would actually require quite a bit of mathematics, right? But you could use op-amps to solve the differential equations for you. Okay, because if you're working on control system engineering or any automation or anything like that, the description of a system or a mathematical model for a system would often be a differential equation, because that's how dynamic systems are modeled. Continuous time dynamic systems are modeled, right? So differential equations. So you would need to solve differential equations, and by solving them manually might take a lot of effort. So people invented something called analog computers using op-amps that were used to solve differential equations. Okay, and we are going to see how people did that back in the day, and this was quite interesting, I would say. Okay, let me bring something. Hold on for a second. Okay, here is a book actually. I bought out of interest. Essentially, this book is kind of obsolete for the most part. Okay, this book is obsolete for the most part. But essentially what it tells you is that how people did simulation. Nowadays we use the term simulation, right? What is simulation? Essentially we write a computer program to kind of artificially generate the conditions and the results of a practical physical system. But back in 1940s and 1950s and 1960s, people didn't have the luxury of buying a personal computer, right? So back in those days, how people worked with simulations and everything, including analog computers, this book actually describes everything properly. So again, these are kind of old historical accounts per se. But back in those days, when people, so for example, just to give you an idea of how things really work. So if imagine it's 1950s, okay, early 1950s, and you are working on an aircraft company, so which actually makes fighter jets, for example. Question is, how would you actually model the dynamics of your aircraft? Before that, people used to do that manually, right? Now you are making fighter airplanes, or maybe standard airplanes like that. But how would you model the dynamics? Of course, you would have differential equations. If you wanted to solve them manually, you would need lot of manual labor, right? So back in those days, what you would do, you would put those differential equations, big differential equations, into analog computers. Okay, and what were analog computers? Hundreds of op-amps. Okay, and we would essentially put different jacks into different places, and that would result into a differential equation solver. Quite amazing if you think about it. Okay, nowadays things are becoming so concealed within our digital realm, but back in those days, people actually saw how things really worked. Okay, in a sense. So we are going to pretty much, again, I told you this subject is going to be mostly a historical account of everything. Okay. Anyway, so this is the DL differentiator, right? Differentiator and integrator, right? So with that said, we have completed one of our important properties here, right? So now we have one more property which we skipped earlier, which would be the frequency derivative property. Frequency derivative property of Laplace transform. So essentially what we are looking for, if again we have kind of the same setting, if the Laplace transform of xt is again xs then we are looking for the Laplace transform of that thing for which we are trying to find out that signal for which the Laplace transform is this frequency derivative, so dxs by ds. Okay, so we are kind of looking for this. Essentially we are looking for this, and this one is again easier to evaluate, because we know that xs is defined, again if you recall our definition, very definition here, xs is defined this way, and this was xt e to the power minus st dt, all right, like that. And if we differentiate the left hand side, what we get, differentiate the left hand side with respect to s, what we get is this one, all right. And again we are differentiating with respect to s, so that will go to the right hand side, and that will become minus infinity to infinity and xt e to the power minus st and dt. And now look at the integration. This integration is entirely with respect to t, so s is a constant as far as the integration goes, so this dds can go inside, and this dds will have no effect on this one because that's a pure function of t. Okay, now this dds will have some effect on this one because this is also a function of s, right? So essentially what happens is this dds actually goes into the integration, does nothing to this xt because it can't, and it actually directly affects the e to the power st term, right? Now if I differentiate e to the power minus st with respect to s, I would essentially get this one. So this becomes minus t e to the power minus st, because we are differentiating with respect to s, so t will be a constant with respect to s. So this minus t can go outside. No, minus t cannot go outside. Okay, the point is I have a minus sign here, or rather I would write something like this. I would have minus t xt e to the power minus st dt, right? Now look at this entire thing. Of course t couldn't go outside because t is a function of t, right? And we are integrating with respect to t. So isn't this a Laplace transform of minus txt? So this is essentially the Laplace transform of minus txt. That's essentially the Laplace transform of minus txt, right? All right, so we can, with that said, we can write it as a proof, and we can say this is just minus txt. Or even better, we can put the minus sign here because this is again a linear operation. We can put the minus sign here. So it says that if I multiply the signal with t, then the output would be a derivative of the Laplace transform with respect to s with a minus sign. Okay, essentially like that. Also there is a corollary which, let me tell you, I mean this could be further. So you could do a further, you could put another t here, and subsequently what you could do, you could check, so you could multiply with another t, so that will be another derivative with another minus sign, so the minus sign will become positive 1. So essentially what we have is, if I have t to the power n xt here, that would be minus 1 whole to the power n. So essentially if n is 1, then that would be a negative sign. If n is 2, that would be a positive sign. And the nth derivative of the Laplace transform with respect to. So that's again a simple extension of this. You can do another portion of like this, and that would result into this. So let's see an example, simple example. Let's see an example. Again, a very simple example we are taking here. For example, so we know that the Laplace transform of ut is 1 by s. Okay, then so we know the Laplace transform of ut is 1 by s, right? Then what is the Laplace transform of tut? What is the Laplace transform of tut? because we are multiplying, we have the same setting, and based on that we would have our time frequency derivative of this. So this is your xs and this is your xt, and we are calculating the Laplace transform of t into xt, so that would be minus dds of xs. Okay, so again we have a minus sign, and the derivative of this is minus 1 by s square, so which is essentially 1 by s square. And what is this signal? This tut is essentially the unit ramp signal, and of course we know the Laplace transform of the unit ramp signal is nothing but 1 by s square. So that's again proves our point here, right? A very simple discussion here. Okay, a very simple example would be this one. Let's take another example, another one. So we know that the Laplace transform of sine at ut was a by s square plus a square. Then what is the Laplace transform of t sine at ut? What is the Laplace transform of this? Again, that would simply be this derivative. Okay, and if we do the differentiation here, so that would result into, so that would be a plus sign. We would have s square plus a square whole square, and with that said, it would be minus 2sa. Sorry, 2sa. Yeah. So if you just differentiate it, so that's the result then. Okay, fine. So we have seen simple examples, right? Okay, and we are left with just one more property here. Okay, again, if you have any difficulty understanding any of these, feel free to ask. So we have one more property. We have the property of frequency integration. Now this property is used in some other contexts properly. I mean, in our control system engineering, I haven't really used this property anywhere. Again, the setting goes, if the Laplace transform of xt is xs, then I'm looking for that particular thing for which, that particular signal xt for which the Laplace transform is this one, right? So I'm looking for, right? Again, I mean, this is not that useful in our particular context here. Okay, in our particular context, this is not that useful really. All right. So again, this is again very easy to prove here. So we're just completing our discussion on the properties of Laplace transform, and then we are going to jump to our proper engineering based discussion. Someone is asking, according to you, yeah, according to someone is asking, is it that according to me Laplace transform is easier than Fourier transform? Yes, Laplace transform is actually easier than Fourier transform, because you don't see those discontinuous functions quite often. For example, in Fourier transform we often see discontinuous functions like delta, things like that, quite often, right? And explaining things become quite difficult. Okay, we did so many convolutions and so many multiplications with delta, right? The unit impulse signal, the Dirac delta, those things are not there in Fourier transform, in Laplace transform. So that's one of the one of the ways in which Laplace transform is easier than Fourier transform for the most part. And apart from that, if you kind of forget all those functions where you had delta and everything, then Laplace transform and Fourier transform, they do have the same complexity. Okay, same complexity. Okay. And again, any problem that can be solved using Fourier transform can also be solved using Laplace transform, but it is not the other way around. but it's not the other way around, that any problem that is solvable through Laplace transform might not be solvable through Fourier transform, because you might have signals, might have functions that are not Fourier transformable, that do not have a Fourier transform, right? But those still might have a Laplace transform. It is quite possible that the signal neither has a Fourier transform nor has a Laplace transform, right? Like yesterday in Python programming class, I told you that if I have a signal like sine of 1 by x, sine of 1 by t, essentially this signal, it does neither have a Fourier transform nor has a Laplace transform. So if you encounter signals like this, you cannot really do anything. Okay, so yes, so in a sense, Fourier transform does not have those, the Laplace transform does not have those impulse functions and everything. So that way it's kind of easier, and Laplace transform is applicable in more general context. But there is one caveat though. The caveat here is that if you are computationally or if you are calculating Fourier transform and Laplace transform numerically, maybe if you are doing numerical computation, okay, if you are developing a numerical algorithm, okay, and if you are given the choice of Laplace transform and Fourier transform, if you are solving a problem through Laplace transform, if you are solving a problem that can be done through both Laplace transform and Fourier transform, and you want to do it numerically, then your better choice would be a Fourier transform, because Fourier transform, because of its certain inherent symmetries within Fourier transforms can be very effectively converted to very powerful and very fast algorithms. And let me just tell you a very fantastic thing. Okay, if I give you two numbers, and ask you to multiply them, of course you can just multiply them, right? But let me tell you a funny thing. If I give you two very large numbers, say for example, if I give you two large numbers so large that they have thousands of digits, right? If I give you two very large numbers and ask you to multiply them, okay, then it is actually easier for a computer to take Fourier transforms, do a convolution, then take an inverse Fourier transform. Doing all that computation would also result into the product of two numbers, okay, two large numbers. But taking the Laplace transform, taking the Fourier transform, doing a convolution in the Fourier domain, and then again coming back with an inverse Fourier transform is computationally easier than just multiplying two large numbers. And for that, if you are looking for prime factors, prime numbers, very large prime numbers, for example, of course there are mathematical researchers that actually try to find prime numbers, right? So those who hunt for prime numbers, and the latest prime number is so big that if you print them in like 8-point font, the set of books would be like 6 feet tall, right? So billions of digits literally. Okay, so yeah, so for those numbers, if you have such a big number and you want to factorize those numbers, again Fourier transform is a better way of doing it, quite surprisingly, because Fourier transform can give you computationally faster algorithms. So if you have a problem that can be solved in both ways using Laplace transform or Fourier transform is the better way to go. Okay, in case you want to do it numerically using a computer, but if you want to do it symbolically using your brain, in that case Laplace transform often is an easier option. I think I answered your question. All right. Yeah, and again, the story is not just for prime numbers. It's if you are multiplying large numbers, dividing very large numbers, yeah, Fourier transform is a better way of doing it. Okay, that's quite funny though, right? Now, how would that be, right? And these things are taught in your digital signal processing classes. And just one more thing, we are discussing continuous time signals and systems. If you are talking about discrete time signals and systems, also digital signals and systems, in that case Laplace transform essentially changes to something called the Z transform, and kind of the equivalent of Laplace transform would be Z transform, and the Fourier transform still remains a Fourier transform, only a discrete version of that or a digital version of that. Okay, so something like that. All right, and funny thing is, Laplace invented Laplace transform, Fourier invented Fourier transform, but Z transform, which is essentially the digital version of the discrete time version of Laplace transform was invented by an electrical engineer. Very funny though. So we are looking for this again. All right. So let's use the definition, very definition of the Laplace transform. Again, that definition is this one. Now we are going to slightly modify the definition. Now again, we are putting a condition. The condition is that xt has now does now need to be causal. So we are assuming here, the assumption is xt is causal again. So we have written quite a few conditions under those properties, right? And so many of the properties are not applicable unconditionally. They do need to satisfy certain conditions before they are applicable, right? Like the final value theorem, like other properties that we did. And whenever a condition needs to be satisfied for a particular signal, particular property to be held true, we did those things. Someone is saying, we think we have to do that transforms as well. Yes, you do have to do that transforms as well. Okay, and digital signal processing is like a combination of your signals and systems, control system, and digital electronics combined. Someone is saying, yeah, someone is saying everything was invented by electrical engineers. See, the point is, there wasn't anything called computer science back in the day, right? So the most prominent computer scientists that you might have heard of, those are either electrical engineers or something like a mathematician. Okay, so computer science wasn't there up until like 1970s. There wasn't really something called computer science engineering and as such. Everyone was electrical engineer. Okay, the first branch of engineering was a civil engineering. So essentially the first branch of engineering was civil engineering, right? Because of course you needed construction, needed different systems in your town, right? So the first branch of engineering ever invented was civil engineering, of course. And then came electricity, right? So the next branch of engineering was electrical engineering. And then came electronic components. So subsequently electronics engineering. Then came computer science. That is how things originated. But mathematics was there in the beginning, right? Okay, right? People, when people lived in the caves, people did not have mathematics. But when they started farming and all, they had their cattle and everything. So they needed counting. They needed a mechanism to count their possession, right? So I have these many cattle, right? I have these many cows, these many donkeys, and all these things. I have to count them. So that necessity essentially gave birth to mathematics. So yes, in the beginning, human invented fire. That is how we distinguished ourselves from other animals, and then we invented mathematics, literally. Yeah, and mechanical engineering used to be considered a branch of just like electronics engineering is considered to be a branch of your electrical engineering. Similarly, mechanical engineering is kind of considered to be a branch of used to be considered to be a branch of civil engineering, a specialized branch of civil engineering. But then again, it actually evolved into much larger things, right? And for the most part, what you call mechanical engineering is considered applied physics. Used to be considered applied physics. Yes, in that sense, mechanical engineering was there from a very long time. But still, the point was it was considered physics, just physics, right? So if you think about it, Isaac Newton was a mechanical engineer, right? He wasn't. He was a physicist. All right. So that's the definition of Laplace transform here. So we are trying to prove this, right? We are trying to prove this. Rather, we are trying to figure out what is that signal for which the Laplace transform would be this one. And let's do this thing. Let's integrate on both sides with respect to S, right? So if I integrate here, okay, so we have again landed into a double integral. Again, don't worry about the double integral thing. Okay, what did I write? Laplace transform of so x is equal to, oh fine, no problem. So we landed into a double integral once again, but don't worry about the double integral. Okay, So we are going to color code them as usual. Whenever we encounter double integral in our class, we color code them to make sure that everybody understands what's going on. All right. And as a standard trick, we're going to change the order of integration here because the functions are kind of well behaved in our discussion. So we are going to change the order of integration. So this integration from 0 to infinity will go outside, and then we are going to have this one, and then we have these signals e to the power minus st, and we have changed the order of integration, so it will be ds, and that would be right. Now this inner integration, look at the blue one, this blue for the blue integration here, this inner integration, xt is a constant because s is the variable of the integration, right? So xt is a constant, so that can go outside this one. So for the next part I can write this from 0 to infinity, I have xt that is going outside, and then we are left with this integration s to infinity, and we have e to the power minus st, and of course we have ds, then we have, sorry, that would be a green one. All right, so let's now do the integration here. So 0 to infinity on xt. And what about this integration? Of course, we are integrating with respect to s, so t will be treated as a constant. So, and again, this will be 1 by t, and the result would be e to the power minus st. Okay, we are integrating. It's a very simple integration, right? And there would be upper and lower limits. Of course, the lower limit is s, the upper limit is infinity. So we have taken care of that. All right, so we have taken care of this integral here. So again, the limits are for s, not for t. So this 1 by minus 1 by t does not have any proper effect here, and I'm changing everything to so we have just a single integral, so I'm changing everything to the same color here once again. So here we have to put the upper limit and the lower limit. So now look at the upper limit here. So when, again, just one more thing, we change the limit from minus infinity to 0. Of course, just keep in mind, since xt is causal, we just change the limits here to the suiting our need here. So now here t is positive throughout this, so t is positive. So in place of s, if I put infinity, then it becomes e to the power negative infinity. So e to the power negative infinity would be 0. Then we have a minus of minus 1 by t, so that's a plus 1 by t. And if I put s, that becomes e to the power minus st. And we have a dt here, right? So you can understand why I chose the lower limit to be 0 instead of being minus infinity. Simply because if I wanted to put s equal to infinity and make sure that this limit was 0, I have to ensure that t would be positive. And how would I ensure t would be positive? I would ensure that by making the lower limit to be equal to 0. And how can I make the lower limit equal to 0? By choosing this condition that xt is causal. And that is why this this property is not applicable if xt is non-causal. All right. So again, now what we have is integration from 0 to infinity. So that's 1 by t xt e to the power minus st dt. Okay. But look at this one. Isn't it essentially the Laplace transform of 1 by t xt? Isn't it the Laplace transform of 1 by t xt? Yes, that is, right? So with that said, that would simply be 1 by t xt. Nice. Nice. So let me show you a very fantastic example here. Very fantastic example here. right? Example. Okay, recall our sinc function. Okay, so we know the Laplace transform of sine t was sine t, Laplace transform of sine t ut. Okay, the unilateral Laplace transform essentially was 1 by s square plus 1, right? Then what is the Laplace transform of sine t by t? So that's the sinc function, right? So that would be this integration from s to infinity on 1 by s square plus 1, right? But what is this integration? Sorry, on ds like this, right? By this property. So this is essentially this integration, and now this integration is tan inverse s. You did study this in your class 12, right? Now if you put the upper limit, that's tan inverse infinity. Tan inverse infinity is pi by 2. So that's pi by 2 minus tan inverse s. So that is, we just figured out the Laplace transform of sine t by t, which is the unnormalized sinc function, also known as the SA function, the sampling function. That's the Laplace transform. So here, this is one example where this is not a polynomial, okay? This is not a polynomial. And there is a popular question. There is a popular question which goes, do this integration from 0 to infinity on sine t by t dt. The thing is, it cannot be integrated directly. You cannot find any primitive or any antiderivative of this one, but you can apply the property here. So the thing is, we know that the Laplace transform of, we just derived moments ago, that the Laplace transform of sine t by t is this, right? So Laplace transform of sine t by t. Let's calculate the Laplace transform of sine t by t. So that's again integration from 0 to infinity on sine t by t e to the power minus st dt, right? But moments ago we just derived that this Laplace transform of sine t by t isn't nothing but pi by 2 minus tan inverse s. So this integral is essentially pi by 2 minus tan inverse s. But just keep in mind, we cannot do the integration by default, right? We can only use properties and do the integration. Otherwise, we wouldn't be able to do this integration manually by default, right? So that's the thing. Now simply put s equal to 0 in this. If I put s equal to 0, then this becomes 0 to infinity sine t by t, and this becomes e to the power 0, which is 1. So integration with this t, it essentially becomes, and pi by 2 minus tan inverse 0, which is 0. So essentially this is the result. So integration from 0 to infinity sine t by t dt, that's equal to pi by 2. Very simple. And also since sine t by t is an even function, if I ask you about this integration from minus infinity to infinity on sine t by t dt, that would essentially be twice the integral from 0 to infinity. And we know this to be pi by 2, so this is going to be 2 into pi by 2, that's equal to pi. And that is why this is called the unnormalized sinc function. Okay, the result, the integral is pi. Okay, if I divide everything by pi, subsequently what happens, the integral value becomes 1 and then becomes the normalized sinc function. Okay, those are discussions on our signals and systems. But again, so that's kind of the end of our journey with properties of Laplace transform. right? Feel free to ask any question that you probably would have. Okay. We are going to end our discussion with a simple problem here. Simple problem here. Okay, a complete problem here. All right. So this is kind of a problem, simple problem for us. Say, okay, maybe we have a system. System is given by the following ordinary differential equation. No, it's going to be simple. Okay, it's going to be simple. I promise. Say there is a system given by the following ordinary differential equation, and let me make sure that it is simple. D2y dt2 plus 5 dy dt plus 6y. Of course, y is the output of the system. You people know that already. Okay, where xt is the input and yt is, okay, let me just increase the page number, where xt is the input and yt is the output to the output, input and output. And yt is the output. Fine. Oh, there are so many questions. Someone is saying, no. I mean, we are going to keep the thing simple, because again, the point stands. If we have a complicated problem, we have better ways of dealing with them. So we're going to learn those techniques. We're not going to make things unnecessarily complicated for our tools. Okay, that is what people did, right? If the scientists and engineers back then wanted to solve a complicated problem, they invented a method to tackle those problems. Okay, nowadays we brute force everything. What is the brute force? Like force of a brute, right? Force of an animal, something like that. Okay, we just have a problem that can be cracked in a suitable manner, but we take a sledgehammer and bang on it like that, so until it breaks. So that wasn't the deal back then. Okay, so where xt is the input and yt is the output of the system. So now problems are, first, find the transfer function of the system. So find the transfer function of the system. Now it might be so that the transfer function is given already, so you don't have to derive the transfer function. In that case, the differential equation will not be given. Okay, find the transfer function of the system. Okay, now second problem is find the output of the system if xt is equal to ut. So if the input is unit step, what is the output of the system? Now when the input is a unit step, the output, if the input is a unit step, then the output is known as the step response. That is, calculate the step response of the system. So again, you people know that. What is step response? Step response essentially is the output of the system when the input is a unit step. So these are the two problems that we want to solve here. Okay. So now solution. Okay. What was the differential equation? Let's bring it back here. Okay, the moment we are saying that we are looking for the transfer function, we are assuming zero initial conditions, right? So there is one again, there is one condition, is that assuming zero initial conditions, right? Simply because we are looking for the transfer function here, right? Assuming take the Laplace transform on both sides. So what you take, if you take the Laplace transform on both sides, what happens? This becomes s square ys. This becomes 5 ys plus 6, sorry, 5 sys plus 6 ys. This is simply because the Laplace transform of xt is xs and yt is ys. So the Laplace transform of the derivative of yt would be sys. Laplace transform of the second derivative of yt would be s square ys. And similarly, Laplace transform of the first derivative of xt would be sxs, and here 4xs, right? Again, if you don't understand this line, let me know. All right. So again, assuming zero initial conditions, so we can factor out ys out of this entire thing. So we would be left with s square plus 5s plus 6, and since we are factoring out ys, so that's what it is. And here we can also factor out xs, so I would have s plus 4, and here we have xs. All right. So what is ys by xs? If you do the division, and so that will be s plus 4 divided by s square plus 5s plus 6. And by definition, this is the transfer function of the system. That is, the transfer function gs is equal to s plus 4 by s square plus 5s plus 6, right? So the first part of the problem is done. Now we are trying to find out the output of the system when the input is a unit step. Let's try doing that. Now, if the input is a unit step, we are trying to find out the output essentially. So let's take a Laplace transform. So Laplace transform of the input is then 1 by s. All right. Then Laplace transform of the output, since we know ys by xs is equal to gs. Okay, we know that ys would be equal to xs into gs. So ys would be equal to essentially xs into gs. Of course, that is the whole thing here. So what is xs? That's 1 by s. What is gs? Forgotten. Okay, again, if you have any query, feel free to ask. That's going to be s plus 4 divided by s into s square plus 5s plus 6. Okay, and just keep in mind, from the next week we are going to jump back into control system engineering. So we are pretty much discussing the mathematics of Laplace transform and all, and then we are going to go back to proper engineering talks. Okay, but I would assume then that you know Laplace transform, because I do not really assume anything without teaching you, right? So then from the next class, I would assume that you have a good understanding of Laplace transform, and we shall build upon that. Okay, so please go through the lectures. If you have to go through them once more, just go through the go through the lecture notes or handouts, as I say, okay, once more at least before attending the next class. Otherwise, you might find that things are difficult to understand, because I shall be assuming that you have good understanding of Laplace transform, because I have taught everything. Okay. All right. So now our objective is to find out yt, right? But what is yt? What is yt? Yt would be the inverse Laplace transform of ys, right? So we are gonna have to take inverse Laplace transform on this signal, right? So we're now looking for the inverse Laplace transform of that entire thing, which is s plus 4 divided by s into s square plus 5s plus 6. Now if you are using Python, you can actually ask Python to solve this for you, right? I have shown you how to actually do that. Okay, you can ask Python to solve it for you, right? But if you're doing it manually, then you have to know how to actually tackle this kind of problems, right? So now the thing is, we could tackle this problem by the very definition of the inverse Laplace transform, okay, by doing that complex integration. And again, I told you, if enough of you are interested, I would do a class on complex integration, right? That would require something called Cauchy's integral formula and Cauchy's residue integral, and from that this can be integrated. And the just to recall what I'm talking about, I'm talking about the very definition of inverse Laplace transform. That was sigma minus j infinity sigma plus j infinity xs e to the power st ds. That's the definition of inverse Laplace transform. I can apply this definition directly here because I know how to do that, okay, and on that I would get an answer. And actually solving this integral, at least for me, would be easier here somehow, okay. And in case you want to go through that, I would tell you later on. Okay, all right. But now what we are trying to do, what we would try to do instead, we would try to figure out the Laplace transform, the inverse Laplace transform, by means of looking at thinking about the Laplace transforms themselves. So what I mean is that we are going to take the partial fractions of this. So recall, this s plus 4 divided by s into s square plus 5s plus 6. Okay, this can be written as, this is essentially s plus 4 divided by s into, this can be factorized as s plus 2 into s plus 3, something like that. And this can be rewritten as a factor a constant factor a divided by s, a constant factor b divided by s plus 2, a constant factor c divided by s plus 3. And the way we treat partial fractions and we calculate the values of a, b and c was created by Oliver Heaviside. Okay, the method we used to evaluate the partial fractions, the coefficients of the partial fractions, were actually created by Oliver Heaviside. All right, so what we do, we essentially try to sum these up. So essentially, if we sum these up, so we would, on the denominator we have the same term, but on the numerator I would have a into s plus 2 s plus 3 plus b into s plus 3 plus c into s into s plus 2. And of course in the denominator I would have s into s plus 2 into s plus 3. So this is the sum of these terms. So we have added these three terms. So that would be equal to this one. That would be equal to s plus 4 divided by s into s plus 2 into s plus 3. I know my head is blocking everything, right? So we have summed up these terms, and that is equal to this one, right? Right, now our goal would be to figure out this constants a, b and c. Of course, for that we would kind of ignore the denominator because they are the same, right? Because they are the same. So we would essentially end up with the equations that are there in the numerator. So essentially we would end up with this. So that will be equal to s plus 4. Now this is kind of an identity. What I mean by that is, this would be true for every possible value of s. This is not an equation. This is an identity in s. This is an identity in S. What it means is that this is not an equation. This is identical. This is identical. Completely equivalent, right? So for every value of S, this should be true. Which means for any value of S, this would be true. So essentially what I mean is that you can put any value, any whatever value of S here, but this will always turn to S plus 4 because this is an identity. And because of that, we can apply the Heaviside's cover-up method. It's called Heaviside's cover-up method. What we essentially do here is that we try to cover up one or more coefficients like that. So if I say S equal to, let's bring this once more down back here, otherwise things are not visible. So you have seen this in your school probably. All right, so now just because this is true for every possible value of S, we are going to choose suitable values of S that eliminates one or more factors completely. So if I put S equal to 0, okay, if I put S equal to 0, then what do I have? I have A into 2 into 3 plus B into 0, since this is 0, plus C into 0, right? So essentially this, and on the right hand side what do I have? Since this is an identity, okay, on the right hand side what do I have? So S equal to 0, so that's 4. But this has to be true always, so the value of A would be 4 by 6, which is 2 by 3. Alright, we are putting arbitrary values like that simply because this is an identity which is true for every value of S. So we are choosing a special case to get these values out, right? Now what about I want to keep this and eliminate everything else. So for that I would put S equal to -2. If I put S equal to -2, this becomes 0, right? This also becomes 0. Then I am only left with the factor with B. So B into -2 into 1, right? And that's identical to, so put -2, so that becomes -2 plus 4. So essentially my equation is -2B is equal to 2, and that gives me B equal to 1, sorry, B equal to -1. So here we have and here let's put S equal to, again now I want to eliminate this, eliminate these two terms, and I want to keep this. So how can I eliminate these two terms? By putting S equal to -3. Alright, so if I put S equal to -3, this becomes 0, this becomes 0, and I am only left with a term, with the term that has C as the coefficient. So C into, so -3 into -1, right? And that's equivalent to -3 plus 4. So this equation is essentially 3C is equal to 1. That's C is equal to 1 by 3. Alright. So now I have done the entire factorization. So let's bring this line back. So that was the whole thing for which we were looking for the inverse Laplace transform, but this can be written as this. We said that now we know the values of A, B and C. Now we know the value of A, B and C. So what is the value of A? A was 2 by 3. That's going to be 2 by 3. What is the value of B? That's -1. And what is the value of C? That's 1 by 3. Alright. Alright. So that's 1 by 3, right? So what were we looking for? We were looking for the inverse Laplace transform of this, right? So essentially we were looking for the inverse Laplace transform of S plus 4 divided by divided by s into s plus 2 into s plus 3, right? So therefore the yt, which is the inverse Laplace transform for s plus 4 divided by s into s plus 2 into s plus 3, would be the same as the inverse Laplace transform for this, right? Because we have just calculated everything like that, because these two expressions are equivalent. Right? Now, of course, since Laplace transform is a linear operation, all we can do, we can simply take the inverse Laplace transform of these individual terms. Yeah, some of you have already done this, right? This is not a difficult problem, as I said in the beginning, right? Of course, these are constants, right? 2 by 3 is a constant, so it can go outside suitably. So that becomes 2 by 3, and we are left with the inverse Laplace transform of 1 by s. Since we are assuming causal systems, what is the inverse Laplace transform of 1 by s? That's ut, because the Laplace transform of ut is 1 by s, since we are assuming causal systems. So again the minus 1 can go outside, so we are left with the Laplace inverse of 1 by s plus 2. But what is that signal for which the Laplace transform is 1 by s plus 2? That's going to be e to the power minus 2t ut, right? So instead of writing minus 1, just put a minus sign, and plus 1 by 3. We are left with the inverse Laplace transform of 1 by s plus 3. What is the inverse Laplace transform of 1 by s plus 3? That's going to be e to the power minus 3t ut. Again, the same thing goes, we are assuming causal systems. Okay, assuming causal. Right? We are assuming causality. So we are just taking ut common out of everything. So we are left with 2 by 3 minus e to the power minus 2t plus 1 by 3 e to the power minus 3t ut. Again, this product with ut essentially means that the output of the system would be 0 if t is negative. Right? So we have calculated the output of the system too. So therefore, the step response of the system which is essentially the response of the system when the input is a unit step. Step response of the system is this signal. All right. All right. So that will be the end of our today's discussion here, and we are going to go back to our actual proper discussion from the next class. Again, if you have any query during the discussion, feel free to ask. All right, so we're going to end our discussion today. This was a relatively shorter class for us. All right, thank you very much, and you shall get the proper handouts, proper exercises, don't worry. Okay, so thank you very much for being here. I'll see you next week. Right, I'll see you next week. Thank you very much.